It feels sometimes like there are layers to the universe. Imagine a scene like you're eating some breakfast. At the topmost layer is your conscious awareness and the decisions you are making. Do you reach for the eggs? Do you reach for the bacon? Do you reach for the cereal? These are decisions you're making. Beneath that layer, there's the macroscopic physics, the motions of your hands and fingers, the momentum of the cereal as it pours into your mouth, the liquid sloshing of the milk. You reach for your glass of orange juice or your cup of coffee, and there's the potential energy change. There's all the macroscopic physics. Beneath that, there is biology. The crunching of the food between your teeth, your salivary glands, your stomach muscles contracting and doing stuff. I'm not a biologist. The peristalsis of your esophagus. Beneath that is biochemistry. There are proteins doing their job of chopping up fats and sugars. There are the acids in your stomach breaking down foods. There are cell membranes emitting some elements and molecules and rejecting others. Beneath the biochemistry is the chemistry, the atomic bonds, the covalent electrons. Beneath that is physics, electrons, orbitals, electromagnetism, strong nuclear forces. Beneath that, atomic physics is the quantum field theory, the vibration of these esoteric quantum fields that subsume the entire cosmos and interact with each other in complicated ways. Beneath that is, well, we don't really know, but that's not the point of today's episode. The point is that there are layers. And we feel like all of these layers are connected, that you can start on any layer and use your understanding of that layer to work your way up. For example, if you understand biochemistry, how molecules and elements interact with each other with your proteins and your DNA and all that, then you can figure out how biology works. And if you understand how biology works, you can use that to understand the mechanics of the choices and actions of eating breakfast. And if you start at an even deeper level, if you go all the way down to the basement to quantum field theory, and if you worked really, really, really stupendously hard, then you could use quantum field theory to describe the action of eating breakfast in terms of interlocking, overlapping, interacting quantum fields. But you can't. I mean, sometimes you can in limited ways. I'll give an example in a little bit. Most of the time, these layers are relatively separate from each other. Think about it. Quantum field theory may help us understand how subatomic particles interact with each other in high energy experiments. It gives us some understanding or a refined understanding of how atoms behave, but it's totally useless in providing an explanation for how acids in your stomach are breaking down your eggs and bacon. Use different tools like chemistry to figure that out. And the key thing is that you can figure out most, if not all, of the rules of chemistry without ever knowing about quantum field theory. Imagine a universe where we never figured out quantum field theory. We would still know chemistry. We would still know how the stomach breaks down food. We would still be able to figure out biology and biological mechanisms, how energy is transported inside the body, all that without knowing quantum field theory. Even though there are layers, they don't necessarily connect to each other in obvious ways. And there's a word for this kind of layering, how one layer, even though we know at the base level, we're all interlocking quantum fields, but we don't know how to use that language of interlocking quantum fields to describe, say, the digestion process of bacon. We can't jump all those levels and use quantum field theory to describe that process. There's a word for that kind of layering, and that word, it's our word of the day, it's emergence. The cool idea behind emergence is that you can have layers to physical systems, and discovering the workings of one layer, say a nice deep fundamental layer like quantum field theory or physics or even biochemistry, doesn't always give you better information or any information at all about how the higher levels work. That's because the properties of the higher level system emerge from lower level interactions in non-obvious ways. Presumably there's some way to make the connection, but it's not always guaranteed. I could go to the world's most renowned quantum theorist, the smartest person on the planet, the deepest expert in quantum field theory, and say, hey, I'm going to give you a physical system and I'd like you to describe it with quantum field theory. And they say, sure, that's my job. And if I say, it's two electrons interacting with a photon, they say, got it. All right. They write down some equations. They're good. I say, okay, now I've got a different physical system for you. The digestion of bacon in a human stomach. And they'll say, get out. How did you find me? We can't. Even though it's all really deep down based on quantum field interactions, we don't know how to express that. As another example, we can know all we want about biochemistry and neurology and how the brain works and synapses and sodium ions and all that, but we can't explain the emergent property of consciousness, can we? It may not even be an issue of practicalities. It may not even be an issue of, we just don't have the sophisticated mathematics or computational expertise or what have you. It may be literally impossible to do this because what emerges out of deeper systems isn't always connected to the deeper system. Let me give you 3 examples to show how sometimes emergence can be understood and obvious, and sometimes it can't. And we don't exactly know how to get out of it. For example, here's an easy example. We have various rules of thermodynamics like temperature, pressure, the ideal gas law, PV equals nRT. Pressure and volume are proportional to temperature of a gas. This is all thermodynamics. These are emergent properties of something else. You can understand the physics of an ideal gas with pressure and volume and temperature and the relations between them and all that without ever knowing what the gas is made of, or that it's made of atoms and molecules interacting with each other at a microscopic scale. It turns out we can, and we can figure it out. We know that, say, the property of temperature arises from the kinetic motions of the gas particles. If there's a bunch of gas particles and they're hitting you, they are delivering a bunch of kinetic energy, and you add all this together and you get a sense of the temperature. There's an entire branch of physics known as statistical mechanics that's really cool and doesn't get nearly enough love in the popular press, that connects the fundamental physics of, say, gas particles interacting with each other at microscopic scales to an emergent property of temperature or pressure or volume. Here's another way of saying this. If you're probably in a room filled with air, I hope you are right now, there's countless air molecules bouncing around. You feel the temperature of the room. Right? You can feel that. That is a quantity you can measure and experience. But if you were to ask any individual air molecule what its temperature is, it would say, I don't know what you're talking about. I'm an air molecule. All I have is momentum and kinetic energy and velocity and position. Maybe electric charge if you're lucky. That's all I got. That's what I know about myself. I don't understand what you're talking about. But if you get that one air molecule together with a quadrillion of its friends, there is an emergent property called temperature that arises from all of their countless individual interactions, and we know how to make that link, and that's super cool. Here's another example. If you take a material like silly putty, materials have properties like viscosity and elasticity. We know that these properties of viscosity, elasticity, stretchiness, bounciness all arise from a complex set of molecular interactions. We know that certain substances are stickier or squishier or bendier than others because of what they're made of and how those particles or those elements interact with each other. Sometimes we can describe these properties of squishiness or bendiness or stickiness from first principles, where we can start with the very basic molecules and then we can look at how they interact with each other and we can build up a measure of how squishy the overall object is. Sometimes we can't. Sometimes we don't know why a certain material is sticky when it's not, when it shouldn't be, or stickier than other materials. We just don't know. It's an emergent property. Heck, explaining why glass is transparent is possible with quantum field theory, but it ain't easy. Feel free to ask if you want the deep dive on that. It's possible. A hard example is superconductivity. All the quantum physics tools in the world can't help us explain why superconductivity, especially at high temperatures, actually happens. It just does. Some materials are superconductors at high temperatures, others aren't. We can't really explain why. So what does this have to do with gravity? Back in the funky 70s, Stephen Hawking discovered that black holes aren't entirely black. They actually leak a little bit of radiation. It's very slow, very slight, but it's there. It's through various complex quantum interactions at the event horizon. Black holes aren't totally black. Okay, don't need to worry about how that happens, just that it does. Nearly simultaneously, another theorist by the name of Jacob Bekenstein discovered that because black holes are emitting radiation, that you could take our laws of thermodynamics, things like language like pressure, temperature, entropy, volume, all the normal properties that you would ascribe to a room full of air, you could actually use that exact same language. Is the weirdest thing, and we do not understand this connection at all, that you can take those exact same properties and use them to describe black holes, and especially the radiation given by these black holes and how black holes evolve. And when they merge together, what happens? That you could make this connection between thermodynamics and black hole properties. I will not get into the details of that connection. Feel free to ask if you'd like. I would love to do an episode on black hole thermodynamics. But just the key point here is that Jacob Bekenstein discovered that once Hawking radiation exists, by the way, Bekenstein almost discovered it on his own before Hawking, so we almost called it Bekenstein radiation, but we didn't, that you can take all this language, you could describe a black hole in terms of its temperature, in terms of its volume, in terms of its pressure, in terms of its entropy, and that you could take all of our normal laws of thermodynamics and apply them to black holes. So this is where things get a little weird, because thermodynamics, pressure, temperature, volume, entropy, all that, are emergent properties. Remember, a box of gas, each individual particle doesn't know what temperature is, but the whole box, you can measure this property of temperature because it emerges from the countless interactions of all the subatomic particles, or just atomic particles if you're dealing with like air. It's an emergent set of laws. They're not intrinsic to the base, the lower level of the physics. They're sitting up at a higher level. They emerge through physics. And here we are taking this emergent property, this emergent language of thermodynamics, and pasting it onto black holes. So here's the line of thinking. Thermodynamics are all emergent. They emerge from some deeper physics. We can write down those emergent laws, like the ideal gas law that you might have learned in high school, or you learned and then probably forgot. We can write down similar laws for the behavior of black holes. Black holes are made of gravity, so maybe this is nature telling us that gravity is emergent, that there's a more fundamental thing happening, something we haven't discovered yet, that's creating gravity, the same way that countless particle interactions create temperature, pressure, the ideal gas law. That what we see as gravity is an emergent property of the universe, that there's some deeper interaction, some deeper physics, some lower level. We thought gravity was on the ground floor. Turns out maybe there's a basement to it, and there's deeper physics happening, and that deeper physics gives rise, it emerges into our experience of gravity. This is the thinking behind a 2009 paper by theorist Eric Verlinde. He asked, okay, if gravity is emergent, where is it emerging from? It turns out with black hole thermodynamics, the most important property, the part of the black hole you actually care about, is its surface, which is the weirdest thing. It's bizarre, and no one expected this. Like if you add information to a black hole, yes, the volume of the black hole goes up. Like if you dump stuff into a black hole, the volume goes up. You add information, the volume goes up, but it's disproportionate to the amount of information you add. Instead, what goes up directly proportional to the amount of information is the surface area. Like the surface area of a black hole cares more about what it ingests than the volume does, which is weird. This is potentially another clue that gravity cares more about surfaces than volumes. And so to put a bow on Verlin's idea that maybe there are some very exotic, very strange, very unknown interactions happening at the edge of our universe that give rise to gravity. We don't know what these interactions are. We don't know what the deeper level of physics is, but that's not important. We actually don't need to know that part because right now, we only care about the emergent part. Just like you can develop an entire theory of thermodynamics, the relations between pressures and volumes and temperatures. You can build gas engines. You can do all sorts of cool things. You can do hot air balloons. You can do whatever you feel like with the laws of thermodynamics without ever knowing what air is made of, without ever discovering the deeper physics. It's cool that we did do that. And we can draw those connections, but we don't need to. You could have an alternate universe where we never figured out that air is made of molecules interacting, and we can still have thermodynamics and all of the technology that flows from that. This is similarly, we don't know, at least right away, what the fundamental, the real interaction is happening at the surface of the universe, what's actually happening. All we know, according to Verlin, is that gravity, our experience of gravity, emerges from it. And it's bigger than that. It gets really wild because gravity is more than gravity. We know this from Einstein. Gravity is the bending of space-time. It's inertia. It's motion. Gravity is intimately linked to our fundamental concepts of existence in the universe. And so Verlin's idea is that something is happening on the surface of our universe. Gravity is emerging from it, and it's not just gravity, it's also space. It's also time. It's also inertia. It's also motion. That everything we associate with our three-dimensional universe is actually happening at the two-dimensional boundary. If this sounds like holographic theory, if you remember the holographic theory episodes from way back when, it's very similar. It is inspired by that, but adds this twist that gravity is an emergent property of interactions happening at the boundary of our universe. In fact, in this view, our universe is entirely two-dimensional. It is just the surface, and there are some really cool, probably quantum interactions happening on that surface, and out of that, a three-dimensional cosmos with space and time and gravity and inertia and motion emerges out of that. So the goal of this emergent theory of gravity is to figure out how to express all of our knowledge of gravity and inertia and space and time and motion in terms of languages like thermodynamics, because we know thermodynamics is an emergent property of the universe. We know that thermodynamics is somehow strangely connected to the properties of black holes. So if we use similar laws, if we take our laws of thermodynamics and recast them, I'm skipping over a bunch of mathy math here. If we recast them in terms of gravity, then we can write down an emergent theory of gravity without knowing what the deeper physics is. And we can do that. Verlin did that in 2009. First glance is, so what? Congrats, you've rewritten gravity. That's kind of cool, but also not super useful. You've just taken what we know about Einstein's gravity, general relativity, and wrote it in a different language. Okay, so you translated it. Good job. But here's where the magic happens and makes emergent gravity even more interesting. After some massaging of the math, which is valid or not, we'll get to that. And then you also introduce the reality of dark energy. Some stuff pops out, some discrepancies, where emergent gravity starts to look different than Einstein's general relativity, where the physics of our universe starts to diverge from what we'd expect from GR. And this actually only happens, and this is what makes it super interesting, is that this only happens, this discrepancy from Einstein's relativity only appears when gravity is super weak. And that's different than the normal approaches to modifying gravity. In all of our searches for quantum gravity, we care about when gravity is super strong, like at the center of a black hole. Now, with emergent gravity, If you recast gravity in terms of this emergent language, and you introduce the reality of dark energy, you start to get differences in gravity when gravity is very weak. You get different gravitational interactions between objects. Like I said, I'm skipping over a bunch of math. It gets very complicated. I hope I'm not insulting your intelligence by skipping over it. How this actually works in the mathematics. I believe that all of you are wise and learned and contributors to Patreon. That's patreon.com/pmsutter. Your Patreon contributions are an emergent property of all of your individual actions, and I truly do appreciate it. The key idea that allows Verlind and others to make progress, this emergent gravity idea to make progress, is that we don't need to know the detailed microscopic processes. All we need to know is that gravity is emergent and it kind of sort of looks like thermodynamics. Then once you add in dark energy, you start to get differences between emergent gravity and general relativity, and that means you can start testing it. One thing that you can imagine that this emergent gravity does is that it makes space itself have properties more like matter. It can have properties like elasticity or compressibility. It can have a little bit of squishiness or a little bit of stretchiness. And this allows space to be able to squeeze in on itself in certain conditions, which gives the appearance of extra mass when there is none. So if you go out in the middle of nowhere, like if you're in the solar system, there's so much mass, there's so much normal gravity, you're never going to see this difference. But if you go out in the middle of nowhere, say between galaxies, when there ain't a lot of stuff, all you're left is space just sitting around doing its thing. And in this view of emergent gravity, space picks up properties like compressibility and it can squeeze in on itself. And so it looks like there's something there because matter is what usually makes space squeeze on itself. But here you've got nothing. Space is squeezing in all on its own. And that kind of looks like dark matter. Right? If I look at a galaxy, it looks like there's extra gravity inside of the galaxy that can't be explained by the visible component of matter. In this view of emergent gravity, what's happening is that once you get up to galaxy scales, space itself is squeezing in on itself, which gives the appearance of extra gravity. There is extra gravitational force inside of those galaxies, but it's not due to an invisible component like dark matter. It's due to the fact that gravity can just squeeze in on itself all on its lonesome in this emergent picture. We have to be careful that this is not modified Newtonian dynamics, that Mond theory where we're going to take Newton's law of motion and start tweaking with it at galactic scales. This is not. This is a completely different approach. This is not trying to modify gravity. This is coming up with a brand new theory of gravity, which is cool. We like cool ideas. We like random stuff. We like getting a little crazy here. Let's run with it. This is the game. And the game has two questions, two sides to it. One, how well do we trust the theoretical calculations? When they make a prediction, say, oh, this is what's going to happen once you get out to galactic scales and emergent gravity, you can say, well, do we trust that result? And then you can also ask, well, once you make a prediction and say you trust the prediction, you trust the math, does it survive experimental observation? Does it survive rigor? And the answer is a little mixed. On the theory side, there are limitations to the math. There are a lot of assumptions that go into a theory of emergent gravity. You have to assume that black hole thermodynamics is actually valid. You have to assume that Stephen Hawking's radiation is valid. You have to assume that the holographic principle holds true, that surfaces are more important than interior contents. You have to assume that you can import this language of thermodynamics and apply it to gravity and it's all cool. You have to assume that dark energy exists and that you know how to fold that reliably into your calculations, because last time I checked, there's no dark energy in like a gas engine. So normal thermodynamic mathematical equations don't usually incorporate dark energy, but now we have to. So it's not super clear how these ideas connect to the real universe, which I know sounds beyond ridiculous because, isn't this the entire point of physics? But with really complicated, really theoretical ideas like emergent gravity, these rest on a lot of assumptions, and it's actually really hard to put it in a physical context in a way that we could observe it or test it. It's one thing to say, okay, gravity may be emergent. Cool idea. It's another to say, this is how stars will behave in a galaxy. Or this is how the cosmic microwave background will look. Taking these super theoretical, far out ideas, which are super cool and we need them and I love them, to actually test them requires a lot of work and a lot of guidance and a lot of assumptions, and you can challenge these assumptions. You can say, well, okay, in a super simplified toy model, this is how emergent gravity works, but I don't know if you can really make reliable predictions about how stars are going to orbit inside of a galaxy, because that's like a kind of complicated situation. And we don't know. Since this is a brand new idea, we don't have decades and decades of experience of dealing with real world situations so we can figure out how the math applies. Like general relativity. Oh my gosh, we got some test cases out early on, but then it took decades to really work out how this theory, all the mathematical tools, really interacted with the universe and gave us robust predictions that we could trust. We could say, yes, general relativity definitely says this about what happens when two black holes collide. It takes a lot to get there. Emergent gravity isn't quite up there. But, there are assumptions. There are some say, there are predictions like, okay, under this laundry list of assumptions, here is how stars should behave in a galaxy. And under those somewhat plausible, I'll give it that, set of assumptions, you get an effect that looks a lot like dark matter, at least at galactic scales. And so most of the tests of emergent gravity have taken place in studies of galaxy rotation curves, of how stars orbit around galaxies. And the conclusion here, after dozens of observations, is maybe. I know, that's what I got. Don't shoot the messenger here. Some studies of some galaxies say that emergent gravity does a better job of describing the behavior of the motions of stars than just a simple dark matter model does. Other surveys, other studies with other samples of galaxies say, no, actually dark matter is better than emergent gravity. It actually doesn't do even a better job at explaining the data. And so there's a little bit of back and forth. There have been some tentative tests beyond galactic scales. There was a study done on galaxy clusters. Dark matter also emerges at galaxy cluster scales where the gas inside of a galaxy cluster is way too hot to be explained by the meager gravity provided by the visible contents. And when you get up to cluster scale, emergent gravity just doesn't cut the mustard. It just doesn't do it. Dark matter is a better hypothesis. It's able to better explain the observations. Dark matter, honestly, it's not the greatest hypothesis, but it's the best one we got, because it can explain so much. It can explain galaxy rotation curves. It can explain the hot gas inside of galaxy clusters. It can explain how galaxy clusters merge together. It can explain the growth of the cosmic web. It can explain the patterns in the cosmic microwave background. Like, it can do a lot of stuff. And a full-on replacement of dark matter, like a theory of emergent gravity, its ultimate test is to explain all the same things that dark matter can, and find little differences here and there so we can tell the difference. Can it do a better job at explaining the universe that we see? So far, it's not looking so hot. That's not necessarily a knock. It's been 15 years since Verlin's original idea. It hasn't exactly fixed a lot of things or improved on dark matter. As theories of the universe go, it's honestly not in the hottest shape, but it's not dead yet. It's still there. It hasn't been ruled out by observations, and so that it can maintain as a contender for explaining our universe. And it can also fall back on, well, hey, we don't fully understand this. This is a brand new idea here. Cut us some slack. We're still trying to shake out all the bugs, find potential mistakes, make sure our equations sit on good, a solid, firm footing. So maybe our predictions aren't that reliable and that we need to go back to the chalkboard, literally, to figure out some more reliable predictions. So there's room here. There's room to talk. It's a new idea. Why does it still hang around though? Because it's interesting. Honestly, and we like interesting things. We like new things. Physicists are like cats. When there's like a shiny new toy, we're attracted to it. Like I said, emergent gravity doesn't just change, doesn't just modify general relativity. It changes our notions of space, of time, of motion, of inertia, of F equals ma. All those properties that rely on space-time. If gravity is emergent, then so is space-time. Then so is motion. Then what we call inertia is an emergent property of some deep quantum interaction. What we call three-dimensional volume is an emergent property of some deep quantum interaction. It's fair to say, like, what we call reality is an emergent property of some deep quantum interaction. That's interesting. Like I always say, if it's interesting, it's probably wrong. But that doesn't mean we can't stop thinking about it. We don't know if this idea of emergent gravity is correct. It relies on a lot of assumptions. We don't know if those assumptions are correct. We're not super confident about the experimental tests. It's a new idea. It's an intriguing idea. It seems to tie together lots of interesting coincidences. And it shows that maybe there's yet another deeper layer to the universe, which is what makes physics so much fun. Thank you to Rebecca H., Talak Raj, Tomislav B., Francisco J., Stephen H., and Kirk B. for the questions that led to today's episode. And of course, thank you to all my Patreon contributors. I can't thank you enough. You have shown so much support over the years. I am eternally grateful. I'd like to thank my top contributors this month. That's patreon.com/pmsutter. My top ones this month: Justin G, Chris L, Barbara K, Alberto M, Duncan M, Corey D, Tom G, Nyla, John S, Joshua, Scott M, Rob H, Lewis M, John W, Alexis, Gilbert M, David L, Rob W, Valerie H, Demetrius J, Jules R, Mike G, Jim L, Scott J, Lewis I, Peter E, David S, Paul L, John Boy, and Scott R. Thank you for everyone, and keep those questions coming. askaspaceman@gmail.com or go to the website askaspaceman.com. Keep going with the positive reviews on iTunes and Spotify. It really helps the show gain more visibility, and I can't wait to get more of your questions and answer more of your questions on the show. It really is a joy to share this with you. I will see you next time for more complete knowledge of time and space.